it'll be a cosmology course, cosmology review, and it will not be a very difficult course, I hope. So what I will try to do is I will try to give you some overview, what's going on in cosmology, without actually going into some complicated calculations and so on. So for example, you will have the whole course, the explorations, on actually doing complicated calculations. So you will do perturbation theory, you will do calculation of power spectra there, and so on. So there are lots of calculations in exploration. So here I'll just try to give you basic ideas, and I'll show you basic disciplines, what's going on. But the first question you may ask is, why to study cosmology at all? And I'll give you at least 3 reasons. And the first one is that it contains lots of very interesting and rich physics. So in some sense, it combines all possible disciplines. It combines, relativity, it combines quantum field theory. It uses, well, it finds applications in string theory. So that's actually the applications of string theory are to cosmology. Quantum gravity, if you want to study the Big Bang and so on. So, combines lots of physics. So it's very rich physics. Physics, like GR, statistical physics, quantum field theory, string theory, and so on. Plasma physics as well. Second reason is that it's a very exciting subject because it's lots of going on in cosmology and lots of things don't match up. So that's why actually the discoveries are likely to be done in this discipline, right? So new physics likely to be discovered here. And let me just quote Zeldovich, who was this famous Russian physicist, and he said that early universe is an accelerator for the poor. So actually, if you cannot, if you don't have the money to build a real accelerator, then actually you study cosmic rays or you study other high energetic events in the universe. And finally, the practical reason why to study cosmology is, and I'll just write it down, is that there are actually jobs in cosmology. Right? So it's much better to study cosmology than, for example, the pure gravitational physics, because nobody's interested in gravitational physics. But lots of people are interested in studying cosmology because new physics is likely to be discovered here. Yeah, so it's a good point to start your career to study cosmology. Okay, so then the plan, which you already have, but let me just very quickly go through it. So basically, it has 3 parts, and we have 3 weeks, so three parts. The first part is just the homogeneous universe. Where I will study mostly the Friedmann-Robertson-Walker spacetime. But before that, actually, I will tell you a little bit about maximally symmetric spacetimes. This will be today, symmetric spacetimes. For example, a sphere is a maximally symmetric spacetime, and it's a building block of your FRW cosmology. So we need to understand what maximally symmetric spacetime is, and then we can go to the full geometry of the universe, which is FRW. And we will first study the kinematics, and then go to dynamics, how the universe actually evolves in time. Part 2 will be matter. And so, well, I will try to explain basically the thermal history of our universe. But in order to describe the thermal history, you need to understand first how actually the thermodynamics works in an expanding universe. So you are used to equilibrium thermodynamics. In expanding universe, well, because the universe is expanding, you don't have equilibrium thermodynamics. But you have almost equilibrium thermodynamics. And what is actually preserved is the entropy. So I'll discuss that here, and then I'll use that to describe several interesting phenomena. So as a nucleosynthesis, very, very briefly, because this is a very complicated phenomenon, and then CMB, and I'll discuss briefly dark matter and dark energy. For dark energy, we'll have the whole course. It'll be explorations in particle physics, probably. And then I'll introduce the inflation. So why it is useful for us. And I'll motivate it by 3 puzzles: the horizon puzzle, the flatness puzzle, and the monopole puzzle. And then I'll describe the simplest phenomenology on inflation in this chapter. Okay, and then finally, I would like to at least spend 3 lectures on fluctuations. And as I said, you will have basically the whole course on explorations in cosmology to study this a little bit more. But what I would like to do is I would like to phenomenologically describe CMB power spectrum. And then return back again to inflation, but show you that actually inflation, so you get more from inflation than you put in. So actually you introduce inflation to deal with, let's say, horizon puzzle. But what you get for free out of inflation is also, it generates the perturbation, the right kind of perturbations, which actually give rise to inhomogeneities, which eventually produce galaxies and produce things like that. So actually inflation as a generator of perturbations. And that's something, which you really get, which is nicely, you don't put that in. It actually comes out as an extra feature of inflation. And if we have time, which we will have not, I can discuss a little bit about structure formation. Maybe you will just discuss it in your tutorial if the time permits. So there's lots of sources you can actually read if you want to. But let me just mention 2 here. So sources. So very nice book is Doddelson. Modern Cosmology. So that's at the right level. It's very readable. It has almost everything. Also very nice is these lecture notes by Baumann. And you can download them, and I give you that link there. And they serve us as lecture notes for part 3, so exactly the right level again. They're a little bit more mathematical than I'll do, but yeah, very, very nice lecture notes. So you may download these. Okay, questions, comments? Okay, no questions, no comments. So, chapter 1, homogeneous universe. And so let me just state a few facts about the universe. And the first fact will be its size. So observable universe is approximately 3 times 10 to the 4 megaparsecs. If you are not familiar with what parsec means, just find it out in Wikipedia or whatever. So this is the size of the universe. And then another fact is that if you look at the universe as a whole, then actually it looks very much isotropic. So no matter which direction I look, it looks all the same in every direction. So, but of course, this is true only on large scales. So averaged over large scales. So this is the total size, 3 times 10 to the 4. So it's about 100 of megaparsecs. Then the distribution of galaxies. So galaxies are basically isotropic. So of course, the universe is different here if I'm on the wall or if I'm in the air. But if I average over large distances, approximately it is actually isotropic in every direction. of course, this isotropicity depends on the observer. So, for example, if you are, let's say I have a fluid, and then that fluid is completely isotropic and no problems, but I start moving within that fluid. So if I move crazy in one direction, then of course I see a flow. The particles are coming at me from one direction, and they are going away in the other direction. So this isotropic thing is actually seen only by very special observers, and these are called comoving observers. Isotropic for a typical, and let's call it freely falling observer. Basically, an observer which is at rest with respect to the cosmological fluid. Right? So if you are moving, then you wouldn't see isotropic. Okay, so now this is true for galaxies, but it's actually even more true for the cosmic microwave radiation. Okay, so isotropy even better for CMB, cosmic microwave background radiation. And there you actually see fluctuations which are of order 10 to minus 5. So fluctuations are 10 to the minus 5. It's very, very isotropic. Okay, so now we established the isotropy. That's an observational fact. And now let's do some, little bit of theory. And then you say, well, we don't have any particular special place in the universe, right? So if we see the isotropy, why not our neighbor who lives in Alpha Centauri or whatever, right? So if he also sees the isotropy, and another observer sees the isotropy, the universe is isotropic from every point, around every point. And that actually implies that it's also homogeneous, which means that no matter where I move, it looks the same. Okay? But of course, this is an assumption. This you cannot measure because you cannot move to Alpha Centauri and measure that actually the observer would see the same thing. Right? This is an assumption, and that assumption is actually called very nicely. It's called Copernicus cosmological principle. Copernicus cosmological principle. And that basically says that, despite what your mother told you, you are not the center of the universe, right? Okay. So isotropy for any observer any, freely falling observer, but slightly apart or whatever. So for isotropy at every point, or maybe better, isotropy, sorry for that, at every point implies homogeneity. Mathematical statement. Okay, so we will take our universe to be homogeneous and isotropic, but only one of them is an observation. The isotropy is an observation. Homogeneity is basically an assumption, if you want to. It's a reasonable assumption to make, but it's an assumption. And of course, this is only true if you are in these average scales, on these very, very large scales. So now if you are very, very small scales, then you know that it's not isotropic, it's different, right? Here it's different than there. And if you are at very, very, very large scales, you don't know because you haven't seen that far yet, right? So this homogeneity and isotropy is definitely true in these very large scales, but you don't know about small scales and scales much, much, much bigger than that. Okay, so now we want to basically describe the universe. So we need our building block will be homogeneous and isotropic spaces. Okay, and these are precisely maximally symmetric spaces. So let me discuss part A, which will be maximally symmetric spaces. And you know, these are spaces like sphere. So let's do it in n dimensions. So we have Sn and Minkowski, of course, and I don't know, hyperboloid. But also very nice spaces like de Sitter or anti-de Sitter are maximally symmetric. So very, very nice class of spacetimes, if you want. And then there is a very elegant construction how to construct these in one go, basically. So elegant construction. And that's through the embedding in n plus 1 dimensional space. Okay. Okay, so before we go to a general construction, let me just do two very simple examples. Okay, so I'll discuss a sphere, which you will laugh at me, and I'll discuss a hyperboloid, you will still laugh at me, but and then you do the general construction and you will still laugh at me, because it's very simple. So example 1, you have just S2, okay, so this is our sphere. We have x1, x2, and x3, and let's say the sphere has a radius rho. Then the sphere is embedded in the Euclidean 3 space, right? So the metric in that 3 space is just dx1 square plus dx2 square plus dx3 square. That's our Euclidean metric. And of course, the constraint, so the surface of that sphere, well, it's just rho square equals to x1 square plus x2 square plus x3 square. Okay, so this is what it is. Now let me differentiate this constraint here. So I get a 0 equals to x1 dx1 plus x2 dx2 plus x3 dx3. So in other words, if I solve this equation for dx3, and let's put square because I want to plug it here, and then I have dx3 square equals to, well, x1 dx1 plus x2 dx2 divided by x3 minus, well, x3 square. But x3 square is rho square minus x1 minus x2 square, right? So it's rho square minus x1 square minus x2 square. Okay. So now I evaluate this guy here. I can plug it here, and that's my metric on the sphere. Okay. So now, of course, you can. So these coordinates are called Cartesian coordinates. You can change to spherical coordinates in the standard way. So changing to spherical coordinates. I'll just get that ds square is rho square d theta square plus sine square theta d phi square. So these are introduced in the standard way. Okay, so that was very simple. So now one more simple, and that's a special kind of H2. Example 2 is the hyperboloid, and basically all you do is that in your constraints you just shuffle some signs. Okay, So shuffle some signs. So instead of considering Euclidean geometry, let us consider Minkowski geometry. So you'll have dx1 plus, dx2 plus, and minus dx3 squared. Okay, so Minkowski. So ds squared equals to dx1 squared plus dx2 squared minus dx3 squared. Okay, and then it has also a, well, let's consider a negative curvature. So then we have plus rho squared. Now we'll have minus rho squared equals to x1 squared. Okay, so these are our constraints now. And so now we proceed exactly similar way. You differentiate this guy, solve for dx3, plug it here, and that's your metric for the hyperboloid. And the picture is as follows. So I have a, if you want, light cone. So this is my x2. This is my x3, which is something like time. And then this thing is rho. And you have two-sheet hyperboloid embedded in Minkowski space. But if you look at that space, it's really a space-like surface here. So it's an Euclidean geometry, if you want. Okay, so it's a two-sheet hyperboloid. And it's embedded in Minkowski space, and it is within the light cone, so it's actually, metric is Euclidean. So it's within light cone. Describes Euclidean metric. Meaning that the signature is the right signature, it's a spatial metric. Okay. So now, well, there's another example, very trivial one. So to a general construction, it's only a tiny step. So now we are in n dimensions and introduce some powerful notation and do all these spaces in one go. So generally, so let me consider n-dimensional maximally symmetric geometry of signature P and Q, and I'll explain what that means, and curvature K, which can take three values, +1, +1, -1, or 0. So +1, -1, or 0. And so this is given by basically the constraint. So first you postulate in which space you live, so what is your basic metric, and let it be eta AB, P and Q, which is a Minkowski metric with P pluses and Q minuses, dxa, dxb, and then this K, which is plus, -1, or 0, times dx n plus 1 square. Okay, and let me define this to be eta big letters A and B, PQ, K, dxa, dxb. I'll just explain what it means in a minute. So this is my basic metric. I'm just embedding in this space. And then I put a constraint, which is k times rho square, where that is the radius, equals to eta AB, PQ, and K, XA, XB. And that's the hypersurface, if you want. Okay, so that is the construction. We call it constraint equations. Constraint equation. Okay, so what is the notation? So here I'm using small letters A and B. So A, B run from 1 till n. The big letters A, B run from 1 till n plus 1. Right, so I'm including the xn there as well. So let me also tell you how to put an index down. So if you have a small index, so xa will be just lowered if this is the small eta ab. So eta ab pq xb. Well, then x squared will be xa xa. That's the notation. And finally, what eta ab is, eta ab pq is just +1, +1, -1, -1, and that is p of those and q of those. Okay. So let's study the space in the same way as we studied in those two examples.
I'm getting because in case of example 2, we
yes?
put minus sign for the dx square, like minus dx3 to the square come from we are interested in cos space. Like if we are interested in like hyperbole embedded in Euclidean space, we would have plus, right?
Well, yeah. You can do other things, but yeah.
But
no,
you say like the curvature k is coupled to the n+1 axis, so
right.
I thought that like n+1 axis is related to the curvature of embedded space. So is the curvature k represent the curvature of embedded space or the curvature of our what is it?
Well, okay. So rho is the radius of your space, if you want, and then they are choosing the sign of the curvature basically by k, right? So in some sense, here I'm choosing positive. Well, k is positive, so I'm choosing curvature like that. And here I'm choosing negative, so it goes like that. But okay, let me continue, and then you can discuss this. Is it okay, or? Okay. So now, of course, with this notation, the calculation is equally simple as for the sphere.
The quick question.
Yeah.
In realistic cases, like, do we have any chance to see more than one negative signature at eta?
Very good question. Thank you for that question. Wait 5 minutes. A very good question. Thanks. Okay. So what we get from here, we have k rho square. Our constraint becomes k xn plus 1 square in the new notation plus x square. Right? X square is that thing over there. So differentiating this is just a constant, so 0. So k xn plus 1 dx n plus 1 equals to minus xa dxa. Okay, and that means that solving for this guy here, dx n plus 1 square equals to xa dxa square over rho square minus kx square. Okay, so that's precisely what we have done for the sphere, but now we are doing for general thing. So of course what it means is that if I shuffle it into the first one, I get the metric, and let me write the metric as GAB. So from here, it follows that GAB, PQ, and K equals to, well, it is the eta AB that's still there, so eta AB, P and Q, and then plus this piece times K, right? So plus K, and if I expand this, it's actually XA, XB, DXA, DXB, right? K, XA, XB, rho square minus K, X square. So the statement is, this is the most general spherically symmetric spacetime, if you want to. Metric for the most general spherically symmetric spacetime. Okay, so now it is a painful calculation to show that if you, so now you have a metric, so you can use GR techniques, right? So you can calculate Christopher's and you can calculate the Riemann tensor, and you can show that the Riemann tensor is actually very simple. R A B C D is a constant times the product of the metrics, so that it has the right symmetries, GAC, GBD minus GAD, GBC. Okay, and if you want, for many, this is a definition of what you mean by maximally symmetric space. And it's such a space which satisfies that the Riemann is proportional to the product of the metrics. And you can read whatever here is related to the curvature. So I'm thinking, but I won't be that nasty to give you this to calculate, so maybe not. Okay. So now what is also very interesting is that, of course, from here you can easily construct what the Einstein tensor is, and you will find out that this space-time satisfies Einstein equations. So I'll be using this notation. I'll put lambda plus lambda on the left-hand side. G mu nu equals to 8 phi G Newton T mu nu. So it will be my definition of lambda. It's on the left-hand side as plus. And then, of course, so this thing solves Einstein equations. Space, of course, T mu nu is equal to 0. T mu nu equal to 0. But once you have this, you can easily construct what G mu nu is, and then find that it solves just this thing here with particular lambda, and that lambda is k times n minus 1 and minus 2 divided by 2 rho square. So maximal symmetric spaces are solutions of Einstein equations with cosmological constant and 0 T mu nu, and this is the cosmological constant. So now to your obvious question. The question is, so this is a general construction, and in principle mathematicians would be happy with any P and Q, right? But as a physicist, you have some requirements, and namely that basically you don't violate the causality, you don't have closed time-like curves and stuff like that. So not every P and Q will do. So we have a table. So let me put P and Q here, and let me put K equals to 0 here, K equal to plus 1 here, and K equal to minus 1 here. So if I choose n and 0, so everything is plus, so I'm in Euclidean space, then K equal to 0 is just the Euclidean space. K equal to plus 1 is the sphere, and K equal to minus 1 is the hyperboloid. So now you can, of course, study geodesics on these things if you want to, but here you know that the triangles have 180 degrees here, and whatever starts parallel remains parallel. Here you know that it's bigger than 180 degrees, and if something starts parallel, it eventually actually crosses. And here it's less than 180 degrees, and whatever starts parallel eventually goes away. Okay, so that's simple and nice. Now let me do n minus 1 and 1. Then here is just the Minkowski. Here is the de Sitter. And here is the anti-de Sitter. So I'll just plot two graphs of these things. And then you might think, well, let's go n minus 2 and 2. But the problem, exactly as you pointed out, is actually, well, mathematicians play with these things, but physicists don't. And the reason is that you actually have 2 times now. And if you have 2 times, you have usually problems, right? So let me put end of story for a physicist, okay? Very good. So that's the table, but yeah, you have them all in one go. So now, de Sitter and anti-de Sitter. Well, anti-de Sitter you will play with in your explorations in string theory, right? You'll study ADS-CFT correspondence. De Sitter is more important for cosmology. So let me start with de Sitter, and you will play with it a little bit more on tutorial. So a picture of ds, and now just doing ds2. So how does it look like? It looks like a hyperboloid in a space where, okay, so t, let's identify t with my x2, and then I'll have x3, and then x1. You know, just use whatever the construction we have done, and then this has a positive curvature, so how it looks like is actually the hyperboloid which goes outside the light cone. So this is your de Sitter space. Okay. It has positive curvature, and because this is well, it's a time-like surface, right? So it has one time on it. It is the Lorentzian metric, right? Lorentzian metric. Okay, so now if you want anti-de Sitter, just take the whole thing and put it on the side. Okay, so ADS2 looks exactly the same, but you just flip it over. Okay, so it looks like this. Now you have light cone like that. This is my x1. Now, this is x3, which is one time. And this is x2, which is another time. So let's put t1 and t2. So if you look at the anti-de Sitter, well, I have one time coming from eta, but I have another time coming from this k. So now k is equal to -1. Okay, so I have basically 2 times. So of course, 2 times is a problem, right? And it is a problem. So how it looks like is this hyperboloid. This hyperboloid here, but you need to see the problem. So for example, if I follow a curve like this, right, then I'm moving only either in time 1 or time t2 direction, right? So actually, I have closed time-like curve, right? Okay, so we have closed time-like curves. So what people usually do is that, well, you may either live with the fact that if you go to the future, actually come back, and that's the usual feature of anti-de Sitter space, or actually you can unwind that and you say, well, I'll analytically continue this thing, and basically instead of going like coming here on the same space of the sheet, you say, well, there's another sheet which continues in this way. So you can actually go around as many times as you want, but you are going on another and another sheet of these things, and this is called covering space. So can go to covering space if you want to. But you see that, you know, anti-de Sitter is very, very strange space-time. So why string theory is like it, I don't know. Well, you know, but okay. You know, an interesting feature of this thing is that the boundary, if you want, I have a boundary, that it's also timeless. So you can have actually field theory living on the boundary, which is the standard field theory, as you know it. But anyway, for cosmology, de Sitter are more interesting. But just remember, I can get one from the other by just flipping it over. Okay? Questions? Okay, so now I have been claiming these are maximally symmetric spacetimes, which means they should have some maximal number of symmetries, right? But here, I haven't used any symmetries in the construction, right? So I just gave you, this is the prescription, let's consider this prescription, and this is what we get. So let me now show that actually these are maximally symmetric spacetimes, or I will not show it, but I'll at least motivate it. Okay, so remember that this was the equation constraint. So the question is, why maximally symmetric? And so you know that the symmetries in GR are connected to scaling vectors, right? So symmetries, again, my favorite scaling vectors. In other words, they determine special directions in spacetime under which the spacetime doesn't change. So now apply new. This is your corresponding Killing equation for these Killing vectors. And now let me ask how many Killing vectors you can have in the spacetime, right? And for that, this is some kind of differential equation. And in order to determine how many solutions you can have, usually study integrability conditions on this. So study integrability conditions. And for a physicist, integrability conditions are nothing else than the partial derivatives actually commute, right? So if I differentiate something again and then I swap the derivatives, I must get 0, right? So this is precisely the thing which we will do. So integrability conditions here, I'll basically differentiate this equation once more and use some tricks, use some, you know, if you have two derivatives of a thing, you get a Riemann tensor out of that. And then, yeah, and then you want to use this equation again and arrive at some condition. So let me just write, starting from the Riemann identity or definition of the Riemann tensor if you want. So you have nabla kappa, nabla mu, acting on psi nu equals to nabla mu, nabla kappa, psi nu, and then the Riemann tensor shows up, kappa mu nu delta psi delta. So that's a definition of the Riemann tensor if you want. So in other words, if I have kappa mu nu, mu kappa nu, and then r kappa mu nu, then what people usually do is that they write cyclic permutations of these indices, right? So let me take this equation with plus, and then schematically I write another plus equation, but I do now nu kappa mu. So then I'll have mu kappa mu here, and the same, and then kappa nu mu, nu kappa mu. So you can write the same equation for these things. And then finally, you subtract mu nu kappa and nu mu kappa and mu nu kappa. Hopefully that works. So now if you add, well, you take these equations plus, and then you take that equation as minus, and you use the Killing equation. So Killing equation tells you that I can basically swap the two indices and pick up minus sign, right? So if I use the Killing equation and I use the Riemann cyclic identity, so Riemann mu nu kappa antisymmetrized, or cyclically antisymmetrized gives you 0. So cyclic identity, cyclic plus Killing equation, and you can do it on your own. Then you find out that if I differentiate the Killing vector twice, I get basically the Killing vector back up to the Riemann tensor. R mu nu kappa delta psi delta. Okay, so that's your integrability condition. And then you can play with this to show it yourself. Okay, so this is very, very powerful equation in some sense. And has many consequences and many applications. So let me just mention one application which is often used in, well, black hole physics, if you want. And that is, if you want to solve, for example, Maxwell equations in curved background, let's say black hole background, then you get it for free if you have a Killing vector in your space-time. Okay, so now how you can see that is that, so consequences. So first consequence is, let me contract the index kappa and mu. Okay, if I contract the index kappa and mu, I get a box on psi nu, and then I will have Ricci tensor standing on the right-hand side. So this will be equal to 0, provided I'm in vacuum. Okay, so that's definitely true. Moreover, if you look back at your Killing equation, and now you construct index mu and nu, right? Then you get twice the same thing, right? So moreover, it's also true is that nabla mu psi mu equals to 0 from the Killing equation, right? Killing equation. And if you stare at these two things, they should be familiar. So this is actually Maxwell equations in curved space, provided I take my vector potential to be my Killing vector. So any Killing vector in vacuum space-time gives rise to a solution of Maxwell equations. Very, very powerful. If you remember your tutorial, the first tutorial in gravitational physics, that's what we used. We said, let's take dt Killing vector in Schwarzschild or curved space-time, and it gives you a solution of Maxwell equations.
Although if you actually have a Maxwell field, then you don't have vacuum, right?
Yeah, so this is a test field solution. It's just I'm solving Maxwell equation in a given curved space-time. You're absolutely right. Yeah, I don't couple it back to gravity. Okay, so that's first consequence. So any Killing vector gives you for free a solution of Maxwell equation. Second consequence is how many are there Killing vectors?
I'm sorry that it was a bit fast for me. Like, how did you connect those two to the Maxwell equation?
Oh,
you didn't write down anything.
Well, okay, so that would require a little bit more work. So, but this is basically like a wave equation, and this is the Lorentz gauge, right? So you know that you can rewrite your Maxwell equations as a wave equation in a given gauge. So now I recover that gauge, and I recover that wave equation. Yeah. So sorry, I haven't. So yeah. So if you want the Maxwell field, well, it's dA, right? D psi is your field strength. Okay. So now killing field is completely determined. Completely by fixing values of, and now you have two, so I have to fix psi mu, and I also have to fix another quantity, L alpha beta, which is nabla alpha psi beta, at any point. Okay, so I'm saying to determine the killing field, all you need to know is to know this and that at one point in your space-time. So why is that? So let's say I have this psi and L at this point of my space-time P. And the question is, do I know how it looks? Can I say what these things actually are? It's another point, Q. Okay, so let's connect these two by some vector field, V alpha, and that's my curve connecting these two things. And then if you look at these equations, so what equations do we get? So first equation is just the definition of, well, it's just the definition of L alpha beta. So if I put psi nu, well, by definition, this is just V mu, L mu nu, right? So that's first equation I have. And that is actually, if you know what L is, it gives you the psi. So now I need the other equation, which is my integrability condition. So V mu, nabla mu L alpha beta, is given by minus R alpha beta mu nu psi nu V mu. Okay, so that's the integrability condition. So now we have two equations for psi and L, and they form a nice closed system, and they are well posed, and they are first order equations. So they always have a unique solution. Okay, so it's a unique solution to those. By the theory of PDEs. Okay, so what does it mean? It means really I can transport, if you want, psi and L from any point to any other point. So if I know psi and L in one point, I know it everywhere. And it's uniquely determined. So to fix how many killing vectors I can have is basically how big the space of psi and L is at a point. Right? Because then everything else is determined. Okay, so that means that on a manifold, I can have at most, well, the space of psi, how many components psi has? Well, n. And how many components L has? So L is derivative of psi. So in principle, could have n squared. But it's not true, because if you look at the killing equation, this is L mu nu plus L nu mu equals to 0. So it is antisymmetric. Okay? So this has only n over 2. Well, the Euler number, whatever the number. So on a manifold, I can have n from psi plus n over 2 from L, which is n times n plus 1 over 2 killing vectors at most. And that's the maximal number of killing vectors you can ever have on a manifold. So in particular, if you are in 4 dimensions, well, it should give 10. And so that happens for the Minkowski space, if you want. So you know that you have 4 translations and 6 rotations and boosts, if you want. So it really, so Minkowski space is an example, and you really know what these killing vectors are. Okay, which time I have almost no time. So if you want to study how many killing vectors on a given space-time, not necessarily maximally symmetric. So this is the upper bound, right? I can never have more than n times n plus 1 over 2 Killing vectors. But for example, for Kerr spacetime, I have many less. I have only 2 Killing vectors. I have time and I have axisymmetry, right? So how would you know that actually in Kerr spacetime there is only 2 and not more? Well, you can actually study these equations by a method of prolongation if you want. And so the method of prolongation, so now you would forget about these V's. And that's a closed system of equations for psi and alpha. So for psi and L, right? So now again, what you do is that you differentiate these equations. So let's say I differentiate this one here. So I put another nabla here. So that means I put another nabla here. So then I will have a derivative of Riemann, and then I will have a derivative of psi. But I can express derivative of psi through this one. So it will be just proportional to L, something like that. So what you can do for a given spacetime where you know what the Riemann tensor is and what its derivatives are, right? I can just put any, okay. So this thing will be something like derivative of Riemann times psi plus Riemann times L, right? So that, right, that's what I just said. So it's an algebraic equation for psi and L, right? So I can start with psi and L having an arbitrary components, and then I can try to solve this algebraic equation, but it gives me some constraints, right? And then, so solving these algebraic equations, you can eliminate components of L and psi as many times as it is possible, and you end up, so numerically you can do it. And in the end, you end up how many Killing vectors actually are in your spacetime. All you need to know is the derivatives of the Riemann itself, you know, and then you just solve algebraic equations. And that's called method of prolongation. It's a very, very powerful method, very nice method. Okay, so 1 minute, very good. So this is how you would find for an arbitrary spacetime how many Killing vectors are. But in the maximally symmetric ones, there are n times n plus 1 over 2. For Minkowski, it's obvious, and you will construct them in your tutorial explicitly. For other D spaces, the construction can be done. And it was first done probably by Schrödinger in 1930s, so you can look it up if you want to. Or it's actually presented in Weinberg's book. So you can, how these vectors look explicitly for our spacetimes, look at Schrödinger's construction. So Schrödinger construction. Okay. So this result, n times n plus 1 over 2, is so important that let me show you one more way how to show it. So if you look in your notes and you see these constraint equations, then some constraint equations is actually invariant. Under the following change of coordinates, so I can introduce x tilde a equals lambda a b xb, where eta ab pq and k equals to eta cd pq and k, and then lca lambda db. Okay, so this looks very much like your Lorentz transformations. It's only that this metric is now a little bit more complicated than the diagonal Minkowski metric, but otherwise it's exactly the same thing. So you can show that these lambdas, so lambda AB actually forms a representation of group, which is almost the Minkowski group, O, P, K plus 1 over 2, and then Q plus 1 minus K over 2. So that's the group, which is the symmetry group of your constraint, if you want. And of course, as usually, you write these transformations like small transformations, so infinitesimally. You put lambda AB equals to delta AB plus small lambda AB. And then you plug it into that equation there, and you find out that lambda AB, when you put the index down through your eta AB metric, it's antisymmetric. So this equation gives you that. Okay. So now the question is, how many of these generators lambda AB are there? So they are antisymmetric, but we are now making the discussion in n+1 dimensional space, right? So there is actually n+1 over 2, which is precisely the same number of Killing vectors you can have there. So that's sort of a proof that these maximally symmetric spacetimes indeed have n+1 over 2 Killing vectors.
Excuse me?
Yes?
What do you mean by that proof for k equal to 0? For k equal to 0, it will be p plus half and q plus half.
Well, okay, so this construction sort of works nicely if k equals to 0, if k is not equal to 0, because the constraint, for example, you don't get any constraint equations if k equals to 0. Your metric is simply the flat metric, right? So basically all this construction is going for k not equal to 0, right? Okay, so questions, comments? So tomorrow we shall start FRW space, and our maximally symmetric spacetimes will be an important ingredient to describe FRW geometry. So see you tomorrow.